Okay, so let's do some simple field theory focusing on force fields. So remember, a force field tells you two different things. A force field will tell you two things about that force: the magnitude, how big it is, and the direction. All right. That also hints at that these things are vectors. So when we want to know how strong that field strength, the direction is easy. The direction is just arrows. So we drew that one when we talk about here's a piece of mass. Right, we want to draw the gravitational field. Gravitational field. I'm just going to shorten that to G field in the future. So if I want to draw the gravitational field around this thing, it's when I put a piece of mass and it's going to get pushed that way. I put a piece of mass here, it's going to get pushed that way. I put a piece of mass here, it gets pushed that way. All right. All right. So you kind of get this idea, and it's the field lines are closer together here, so they're stronger. They point inward. So field strength, if we're looking for the value, the magnitude is the force per stuff, the thing that interacts with the field. So field strength. So here I have a G field. So the gravitational field strength is going to equal the force per mass. Because in this case, gravity is exerted by mass. So let's give some that. So force is F, mass is M. The G field, let's call it G. So now what ends up happening is if I take this and look at it a little bit closer, I have move this around. F equals, mass times G. Hey, wait, I know what that is. That's on Earth. All right, that rounds out to about 10 meters per second squared. But wait a second, it needs to be force per mass. That's exactly the same as newtons per kilogram. So lowercase g is exactly the same as a gravitational field. So now when we look at this, I can call this my gravitational field strength, G. Now let's go to something a little more comparative. Let's talk about the electrical field. Or in this case, I'll call it the E field. So let's have a little positive charge sitting here. Instead of a piece of mass moving around, let's use something else. Let's use another positive charge. So if I put a little positive charge here, it's going to get pushed that way. Put a little positive charge here that way, it's going to get pushed that way. Put one here. Pushed that way, put one here. Push that way. Pretty soon I can connect these together. And now I have this E field. Now by symmetry, it's got to be some force per stuff, but what's my stuff in the electric field? It's charge. So if I move this around, F equals EQ, where E is the electric force, the electric field strength, where E is newtons per coulomb. So as I move this around, F equals EQ, so that means the electric field is then force over charge, F over Q. The electric force F is K Q1 Q2 all over R squared divided by Q. That Q goes away. I end up with K Q1 all over R squared for the electric field due to a point charge. So my electric field pushes out. This is how I can calculate it. Fields are just times whatever stuff you have. Nice and relatively simple. We'll come back to this later.